The resnet architecture was able to improve the performance of VGG by introducing residual connection. This led to deeper, more performant networks. An important question to ask is whether resnets were more performant because of the residual structure of their connection or because the network implicitly created subpaths of different lengths. Dr. Gustav Larson thought that it had to do with subpaths of different lengths and that the residual aren't even that important. The first hint that the subpath was more important came from stochastic depth, a technique to train a residual network that drops a whole layer with a linearly decaying probability. By modulating the length of the network, you can create resnets with smaller amount of layers but much better performance. The second hint that it was indeed the subpaths of different lengths that improved the performance of the resnet came from DenseNet, which was concurrent with the publication of FractalNet. It's a variant of ResNet without the residual addition that instead concatenate the feature and move them forward, effectively exposing all the features to all the layers forward. This simple change from addition to concatenation led to much stronger network based off ResNet. In this tutorial, we'll take a look at FractalNet, a methodology to create what's called ultra-deep neural network without residual connections. We'll also take a look at a Pytorch implementation at the end. The objective that the author set forth here is to design a competitive architecture that makes use of subpaths of different lengths, but has no residual connection possible. The way the author achieved this is by creating what they call the fractal architecture. In this setup, there are multiple paths. Every element within the block has a convolution filters and a nonlinearity attached. Network make use of fractal expansion rules to build the structure that we see on the right. The fractal expansion rule looks like this. It involves three main components: a convolution, a join operation, and an expansion of the previous function. The convolution is pretty straightforward. In FractalNet, we use mainly 3x3 convolution. We also use a 1x1 convolution for some of the results, but for the most part it's 3x3. The join operation is an element-wise mean between n amount of paths. At first glance, this looks a bit like the residual addition operation. However, the element-wise mean is different than the residual addition operation, pictured here at the bottom. In the architecture, we'll see there is no distinction between a pass-through and a residual signal. We just have different paths. The regularization method we'll see later also forces each join to work on its own and not depend on other signals. Finally, we'll see in the end result that the other managed to extract single columns from the architecture with no possibility for residual, and it still works very well. The expansion involves repeating 2 times a given function, which in the base case is a convolution. If we take a look at how the fractal expansion rule behave, we'll get the following. First, as the base case, we have the function being equal to a convolution operation. Then, this is expanded upon to give one path with a convolution and another path with 2 convolution chained together. Both are joined together at the end with a mean operation. That blob here is then expanded upon with a convolution element added on the new path on the left and the blob chained twice together. Now that we create a 3 path, we join them together again with a mean operation. Finally, that big orange blob is creating another convolution element on the new path and chain itself twice. This effectively creates 4 paths that are joined together at the end. Every time this is repeated, it creates a new path. The important variable to keep in mind for the fractal are C, which is the number of column. Here in this example, it's 4. We have B, which is the number of block. In this example, it's 5. As a side note, in the code, it might get a bit confusing because uppercase B is also used to refer to the size of the mini batch. Between each blocks, we have a pooling layer that links them together to reduce dimensionality. At the end of the network, we have a classification layer with the softmax for the different class we'll be training on. The depth of the network is defined by the number of convolution layers on the longest path. It's the formula b times 2 exponent c minus 1. In this example, we have b equal 5, and we have 8 convolution layer on the longest path for the block. Therefore, the full depth of the network is 5 times 8, which is 40. There is 2 ways the author regularized this particular network. Dropout, which is simply dropping some of the neurons in the convolution block, and drop path, a new regularization scheme that the author created to increase the diversity of subpath trained upon. Both drop path and drop out purposes to prevent co-adaptation of activation across neurons, which in turn prevent overfitting. The way drop path works is that it will drop input of the join layer randomly in 2 ways, local drop path and global drop path. Let's take a look at 2 examples. The local drop path works by having a probability of dropping the input at every join. We ensure that at least one path survives so that we don't have a signal just dying in a fractal block. In one instance, it will look something like this. As you can see, local dropout create diverse set of path permutation. The global drop path is a bit more aggressive and only let one column from input to the end survive. In one example, for column 4, it will look like this. This is a very useful way to extract column after the training is done, but this is used throughout the training procedure. Both methodology for drop path along with dropout were used. For drop path, the author had a mix of 50% local and 50% global per mini batch. One thing to consider when doing drop path is that the signal need to be rescaled properly while computing the mean only on the input that are alive. We'll see that in a few. The main difference between drop path and stochastic depth is that drop path has much larger structural diversity than stochastic depth. Since stochastic depth doesn't have this branching structure per block going on, but instead has a probability of dropping out per layer, the network will roughly look similar per mini batch. The training procedure for the FractalNet is stochastic gradient instead with momentum. Batch normalization is used in the convolutional block. Local dropout probability is set to roughly 15%, and then dropout is linearly decaying from 0 to 40%. One of the datasets used was ImageNet, which is a 1000 class dataset used for image recognition problem. Then we have Cypher 10 100, which are 60,000 image with 10 or 100 class. Finally, we have the SVHN dataset, which is 600,000 image of house numbers from Google Street. So the result comparing all the network together look like this. We have FractalNet at the bottom. The first observation here is that DenseNet is way more performant, and they also do not use the residual connections, that they use concatenation. Since it was concurrent with the work, we'll remove it from the analysis for now. We see that FractalNet, even with that, wasn't reaching state-of-the-art result anywhere. However, they were significantly better than the regular resnet, which at the end was the point of the study. As we can see, 34-layer FractalNet was more competitive than VGG and resnet of similar size. This is aligned with the other hypothesis that it wasn't the residual nature of the network that was helping, but instead the training of subpath of different length. Fractal network could furthermore be trained to a larger depth of 160 layers. This means like 6 different subpaths per fractal block, however to diminishing return as the network was overfitting a bit. A very interesting phenomenon here with fractal network is that you can extract one of the column at the end of the training and get better result than a plain network of similar depth. There's some kind of teacher-student phenomenon going on here. How they achieve this is by taking the deepest global path for a column, extract it, and then across all the blocks. That trained column can then be used for testing. If we look at the result in more details, on the left we have the plain networks, so VGG type of network. After 20 layer, there is a diminishing return training network, with the error rate of the 40 layer network is much higher than even the 10 layer network. That's here, what we see with the blue thing, is a degradation problem that ResNet sought to fix up. On the right, we see the whole fractal network with the 40 layer in purple, along with each of the column extracted at different layer size. As we can see, column 4, which has the highest density of convolutional filter, is performing just as well as the whole fractal network and better than the plain network with 40 layers in dotted blue. So effectively, it's bypassing the degradation problem without residual network and with a singular plain network at the end. Okay, now the fun part. We go through a non-official implementation of fractal network line by line. Since it's a bit of a tricky architecture, let's first take a high-level overview of what we'll be seeing. At a glance, there are 3 main components of the fractal network. We have at the top level the fractal net, which will encompass everything. Then within the fractal net, we'll have the fractal blocks. These contain the join operation as well as the mechanism to do the drop path. Then we have the convolution blocks. These are contained within each fractal block and make up the architecture we see in this image. So let's start with FractalNet. This class will be mainly about generating fractal blocks and adding pooling layers in between. One thing to note is that the global drop path will originate from the FractalNet class, not within the fractal blocks. The way the global and local drop path will be implemented is on a per sample basis, not on a per batch basis. This means that for each mini batch, we'll cut the batch into 2, following a proportion pre-established as a hyperparameter. We'll then do a global drop path on the first part and a local drop path on the second part. The fractal block is the crux of the implementation. It's where the most of the complexity lies because of the fractal nature of the network. It is being expressed right there. Instead of trying to implement the figure on the left a useful way of thinking about FractalBlock is as a grid. As you can see on the right, we have the same representation but without the stylization. Two things to note with this grid. There is a join at every layer. It's not obvious, but there is. The join, the element-wise mean here, of a single element is still a single element. So it's redundant to actually see it and show it into the image, but still a join on every layer is there. The second important thing here to note is that the convolution filter density is skewed to the right of the grid. This means that programmatically, it shouldn't be too complicated to know which element to join together if we know how many elements there are within a row. And this is how it will be implemented in the code. Finally, the convolution block is fairly standard. It's just a contained batch norm, ReLU, and dropout operation within a single class. Before we jump into the code, some disclaimers. The code is a bit hard to understand because it's not an official implementation, because FractalNet is not a straightforward sequential neural network. The fact that there's branching going on in the structure make it very hard to reason, and also there's very little documentation on the implementation we'll see. So we'll go very slowly. Okay, let's jump into the code now. Okay, so here we are in the GitHub repository. You can see here we have Fractal Network. You can take a look at it if you want to. Most of the code was taken from this repository over here, of this guy that implemented FractalNet, and that actually I believe that he reproduced the result also. The implementation is pretty decent, so we're going to go through this and then we're going to break it down. Actually this part, the fractal.py, I didn't remove anything in there. I just commented the whole part so that we can understand from top to bottom what is going on. So this is fairly verbose. There's a lot of stuff in there, but we're going to go, like I said, line by line. So overview of the code, fairly, like I said in the deck, we have the FractalNet over here, which is composing the fractal block, which is in turn using the ConvBlock over there, and then everything is in Pytorch, and we're doing a per sample drop path, so not per mini batch, but within the mini batch we're going to cut it. So let's take a look from top to bottom. So first off, the model is created like this. We have FractalNet, and then we have a whole slew of parameters. There's a lot of them, and it's not really standard in how you can find model implemented in Pytorch, but it's pretty good. So first, remember this image. Don't think about the thing on the left, think about the thing on the right. It will make way more sense this than this thing. This is too difficult to reason about. Most of the code is written by taking into consideration that you have a grid and everything is right skewed. So let's go with FractalNet. So FractalNet here we have a constructor, we have a good documentation, which is neat. And then we have here where we're initializing the stuff. Here we're creating all of the FractalBlock layer and applying like the pooling things if we need to. And finally here, this is where we're creating our final classification layer. And there's an initialization going on here per layers. So that's the usual initialize, create layers, and then classification, then initialization of the layers. There's the forward function here that looks a bit different than usual forward function, but we're going to take a look at it afterward. Okay, so the parameter of interest here are data shape, so the shape of the data. We have a number of columns that we want, the initialization channel for the first images that we're going to get, the probability of a local drop. So this is only for local drop path. We have dropout probability. So this is only for dropout, right? So it's regular dropout, not drop path, global or local. And then we have the G-drop ratio here for global drop path. So only for global drop path here. Then there's a whole bunch of parameters that the other use of this code to kind of test different thing. Consist G-drop, don't think about it. It's just to have a consistent G-drop throughout. And then here it's the dropout position that we could do different permutation for dropout, not drop path, dropout. Then there's other stuff that are a bit less important. You can check them out if you want, but this is again is only for properly replicating the paper. Okay, let's take a look at the constructor in depth now. So we have all of this blah 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 that we said. So the parameter is initialization. At first, it's fairly trivial. We're not going to go too much into it. We're going to jump straight into the layer creation. So we have layers here, which is a module list. So it's a list that we have, And then we're gonna iterate on each of the block we need to do, and then create the block. You can see here we're iterating on the dropout probs. I mean, it's good because it actually says how many block we have, but it's not fairly obvious that this is actually what we're doing. We're iterating on the blocks, but this is what's happening. We're iterating on the blocks through the dropout probs. So here you see here the fractal block thing. This is what we're going to dive into in a few, and we pass all the parameter we need to pass to create a fractal block, and then we're going to append it to the layers that we're creating here, the model list. And then we're going to do two things here. We're going to either do a max pooling or adaptive average pooling. So nothing too complicated here. There's a gap variable that will tell us if we are doing this or the other one. It's not that important, but here you can see we have fractal block and then we have pooling going on. And then that's pretty much that. After that, it's just like some information in order to bring in the important parameter to the next iteration of fractal block. At the end here, we're doing the either this one for the prediction layer or this one. This is a linear. This is a 1-1 conv with adaptive average pooling. Both are fairly similar. So if we summarize this whole thing that we saw, it looks kind of like this. We have the blocks, and then we're going to iterate per block. We're going to create one fractal block with the right parameter. We're going to append it, and then we're going to create the right pooling layer, and then we're going to iterate and iterate and iterate. And once we're done here, we're creating the prediction. That's it for the layer creation. Like I said, FractalNet, the class, is just kind of a constructor that align all together the whole thing. And the FractalNet class is sequential in nature. There's no branching happening in FractalNet. It's in FractalBlock that branching is happening. Here we have the initialization, right, to initialize all of our layer properly. It looks a bit weird, but it's fairly standard stuff here. Then we have the forward function. So forward function is pretty important because there's a bunch of variables for global drop path that goes pretty deep in terms of nesting. So we just need to spend a bit of time here to understand what's going on. We have GB over here, right? Which is not obvious, but like this is global batch. And this dictates how much of the batch we should give to global drop path. So this is why we have like the size of the batch here. And then we have the dropout, the global drop path ratio here. And it will give us like the size of the drop path that we want for the global portion. The rest will be assigned to the local drop path per mini batch. And then we iterate on each of the layers that we have and that we have saved. And if it's not a fractal block, we're just going to take the layer, the input, and then putting it into the layer. And this is usually for the classification stuff or for the pooling. If it's a fractal block, we're going to do two things. So don't worry too much about self-consist G drop. Assume it doesn't exist, right? So we're going to do global columns here, and then we're going to do a random integer from 0 to the number of column of the size of this, the chunk of the mini batch that we have. Effectively, this global columns, what it does is that for each of the sample in this section of the mini batch that is assigned to global drop path, we're going to assign a column that we're going to save. That's what it means. It will be used in FractalBlock way down in order to select the column signal that we want to save. And then we just pass the input into the layer, and then we get the output. And we iterate. So that's that. So let's take a look at the FractalBlock now. So we have here a good documentation again. We have a bunch of initialization, some dropout happening. Then we have the columns here, which is a module list of module list. So we have this grid kind of going on. This is based on the columns. And then here we're gonna have like all of the creation of each of our ConvBlock per layer. So we'll follow the image that I've shown earlier. Then we have drop mask, which is going to do the global drop path and the local drop path based on the mask that we're going to apply on the grid. We're going to go through it in a few. And then we have join, which is basically to calculate the mean on the right number of path. We have the forward function, which is a bit complicated because you have to forward all the elements through that grid. at the same time, kind of, and there's different manipulation you're gonna do and different join that you're gonna do per column. Yeah, that's kind of what's happening here, and that's it. So we're gonna go like slowly here. So first the constructor. So for the initialization, we have all of the variable that we're putting here. There's the dropout stuff that we're gonna put. Dropout will make a comeback in the convolution block, right? We're only going to do dropout here if one of the parameters is selected to do a fractal block, then dropout at the end. Not too important here. And then these are the inputs that are given to the constructor. So pretty much the same stuff that we have at the top with the fractal network. There are a few weird variables here that are not well documented. So the doubler thing that we saw, so the max depth here, this is the 2 exponent c minus 1 thing that we need in order to go through this grid. And then this count thing. This count is, I would have called it like row count instead of count. Because what it does effectively is going to count how many convolutional filter you have per row in your grid. But this is useful because, like I said at the beginning, the whole grid for fractal network are skewed to the right. So if you know that you have a convolution block in one row, you know where this element is. It's at the last column. If you have 3, you know which one doesn't have anything, which is the first one, right? Because everything is skewed to the right. There's no holes in between the element, the convolution element. It will make more sense in a few. Here, dropout, fairly simple. And then here, this is the column creation stuff. So we're gonna go slowly here. Like I said, this column things is super important because it's gonna create this grid, and then we iterate through this grid. So we're gonna go self column, so this grid, and we're gonna take a row, like a column out of this whole column list. So effectively, we're taking an array. We're taking the first array here of size and number of columns. Okay, so we're going to iterate from the first depth, so closer to the input, to the max amount of depth. And here what we're doing is there's this weird thing of I plus 1 modulus distance here equal 0. So this, it will be an important. If we are not in this range here, if the dist is not equal 0 with our current depth, we're just going to set the module to none, right? And this makes sense with how dist was initialized. And by the way, dist, I don't think it's a good name for this. Maybe like a distance from the top. I don't know what's the rationale here. But what it means here is that for the first column, we're only gonna add a convolution block at the end completely when I plus 1 modulus dist will equal to self max depth here. When this happens, then we're gonna add. So for the first one, we're gonna go and put the convolution block right at the end, just before the join. And then here you see every iteration in this for loop for the column here, we're gonna have the dist by 2. So this is maybe it's called like this because it's a distance until a convolution between convolution block. And at the end completely, when we're at the last column, the dist will be equal to 1, right? So every time for every row, we're gonna actually put a convolution block. And you see here the convolution block we're creating here, we're creating the module, and then we're gonna append it here. So there's gonna be a bunch of none or a bunch of convolution block, that's it. And every time we're adding something in this row, we're gonna add a count to it. This is gonna be useful afterward in the join and in the drop mask function. Okay, so if we're to simplify this, you have this self max depth, we have this add the module, else don't add the module, and then this have it by 2. This is a division of the distance by 2, and you put it to equal, and it's an integer division, right? So the important part here is that here this is where the dist is equal to the max depth, right? Here is where dist equal max depth divided by 2. You see we put 2 here, and everything else is none. And here is dist equal max depth divided by 4, and this is where dist is just 1. So every time we're gonna add a convolutional filter here. So let's jump into the forward function, and then it will make sense what's happening in a join and in the drop mask function. So here we have a bunch of stuff that is not too important. We're seeing that we're taking the input that we have, x over here, and then we're going to put it into an array and then multiply by a number of columns. So effectively at this point, when we're going to go and do the forward function, we're actually going to push forward like n column number of output that will change differently depending on what they encounter in their path. So over here we have an important variable st that is called. We're going to see it in a few, and then we're going to iterate over there to actually put the stuff into the right module that we have, right? You see this column grid thing? We're going to take the right column with the right convolution block or none from this, and then we're going to put our input over here in there, and we're going to iterate on all the input for the current depth that we have. So we go row by row and push the information in. Then we're going to join every time. At every layer we're going to join. So this is important. Like every layer we're going to join the whole thing. And this we can do that because we don't have to worry about the none, because the out that we're going to create here, if you see here, only going to append in where there's convolution block because of this weird variable called st. We're going to go in a few. That's it. And after that, we are going to put whatever was joined, right, into the output. So this, like every mean that we had over here, we're going to duplicate it into all the outs that makes sense and use that for the next iteration. And here, this is where we're doing dropout if we selected fractal block and then dropout, but this is not too important, you can ignore it. And at the end we return the output for the last join that we're doing. So st, what does it mean? I have no idea, honestly. I can't tell you what st is, but what it effectively does is let you know which is the starting index for this particular row you should start to look at, because it used the count thing. Remember the count here? Let's say for the first one, count will be 1 for the first row. So if we're doing the number of column 4 minus 1, we're going to start at the index 3, which will be this index. You see? So we're just going to do that. If we're in the row 2, the count will be set at 2 because there's 2 convolution blocks at this row. So we're going to do 4 minus 2. We're going to start our count, our iteration in whatever we're doing here. You see? We're going to do this and then that. Same thing for 3 here. Same thing for 4. We're going to do that. We're never going to be in a situation where we're touching a none over here in the grid. So the fact that everything is skewed to the right make it much more manageable. So if we take into, for instance, this one, the row equals 0, we're going to do 4 minus 1 equals 3. And then in this range, we're going to do from 3 to 4. That's what it's written if I replace the variable. Current input will be outs at 3, right? So outs over here. So here basically the input that we got. And then we do current module. We're going to take the right module from the columns over here. And then we're going to append from at the current output that we want the result of jamming this thing into the current module. So this is going to be a convolution block because we're here, right? And then we're going to do self.join current out global column. We're going to put this variable there, and then this output could be there. Here, there's a join at every row, always, right? So I didn't, like the yellow thing that I've put here was a join, but there's a join here, there's a join here. The only thing is that a join with one element is just the element out, because you do the element summed, which is the element, divide by 1, which is the element. So we can do a join here, 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 here. It's a bit wasteful in terms of computation, but it doesn't matter in the grand scheme of things here. So basically, like there's no need to have for loop here since we're doing only one iteration, but it simply look like this. It's fairly straightforward. And then if we have more, then you're gonna move these outputs one by one together. And like, it doesn't matter if these are not touched, you're just gonna do no computation here. They're gonna be passed as they were over there. Same thing for this one. For the next iteration, it will just be passed as it is. Nothing will change. Okay, so let's take a look at join here, how it works. Remember, we're gonna get the global columns that we talked at the way back at the top. It's still not gonna use it. It will still gonna just feed it forward to drop mask. We're gonna see it. So here, what we have the output of to join together, and we have the global columns for the drop path. And if we're not training, we're just gonna do like the mean thing and with no drop. But if we're training, we're gonna do a whole bunch of stuff. So we're gonna first call drop mask, which will give us a mask, right? Like a Boolean mask with zeros and ones. And then we're gonna apply this mask to the out here. So basically, like some of the input that we get, we're just gonna not care about them and put them to 0 effectively. And then we're gonna calculate the mean on what we have left. And how we calculate the mean is with the number of alive here, right? For this, this row that we have. And then we calculate the mean. So here is the sum of the masked out element divided by the number of stuff that are alive. And then we're done. So this is the mean that we're doing, and then the mask. So let's take a look at the masking. So this is how it's used. So we have the size of the out, so the batch size here. We have the global columns and the number of columns that we have in total for this particular masking that we have. So it's the code is breaking into two. So we have first the global drop mask that we create, and then a local drop mask. And after that, we return. So basically what we have is this global drop mask, we make the global drop mask, and then we do the local drop mask, and then we concatenate both together, right? So concatenate so that all of the sample will have some sort of mask applied. So here it's a per sample basis, and then we're going to return that drop mask. Okay, so this is the crux of the whole analysis for drop path. The global columns come directly from FractalNet way at the top. And then what we're trying to do here is only save the columns that we have that matters here. And here, every other signal would just be cut off and be applied a 0 in that mask. So in our example, when we were at the first row here, and we have 4 columns, we're going to do 4 minus 1 for this quantity. And then we're going to do global columns minus 3, basically. So only the ones that have a 3, right, will be saved in this particular scenario for global drop path. So that's kind of what it's saying. Everything else will be set to 0. And it makes sense because at the first column, if we have 3, we're gonna just pass this thing. If we don't have, if we're not at 3, it doesn't matter what we have in the other numbers because we're not even passing through anything, right? So that's the idea. So we're creating our mask here per sample, basically because we have GB. So we're doing all the sample at the same time for all of the columns that we were looking at. And then we're creating the drop mask here by flipping all of the ones that we need to save that fit this quantity to 1. That's it. So that's the global drop mask that we have, and you can test it with like on different rows because the grid is skewed to the right, and because we have a grid, this actually work. It's a bit convoluted, but it works. Then we have the local drop mask, which is going to take and create a local drop batch based on the total batch that we have minus the global drop batch. And how it works is that we're going to create the random binomial here, 1 or 0, and then with the probability of local drop path. So sometimes we're not even going to do drop path, sometimes we do. And then we're going to count the amount that we have alive. And this part of it here, right, is only when we have everything dying, right? When we have everything dying, we're going to flip 1 back on by doing this, right? We're going to do local drop mask, we're going to take a random indices, and then from these dead indices that we have, we're going to set it to 1. And then we're going to concatenate the two, the global drop mask and the local drop mask. That's it for the fractal block. It's very, very nested and a bit convoluted, but in a nutshell, this is fairly clean. The ConvBlock is pretty straightforward. Here we have, it's basically a way to do dropout batch normalization ReLU. And I think Data did that just so that they have more control about the padding type, the dropout position, all this. So let's look at the constructor first. We're just setting up all we need for the forward function here. And it depends on the different parameters. So this is the parameter for the padding, and then we have the parameter for the dropout, if we even do dropout, and then we have what type of batch normalization we're going to do. And in the forward function, what we have is we take the input, put into the padding, whatever we decide, put it into the convolution, and then if this is the dropout position we want, we can do dropout. Otherwise, it's at the end, right? It's just like either before the batch normalization value or after batch normalization value. And in between, we're going to do a batch normalization and end value, and then we put it up. And that's kind of that. There's nothing too complicated in the convolution block. And we're done. That's it. That's the whole thing. All right, everyone. I hope this was a useful tutorial to understand fractal network. Do let me know in the comment if you have a particular request for a deep learning architecture you want me to do next. If you have a question, comment, don't hesitate to post it down below. And I wish you all a great week.